Hey guys, and welcome to this interactive answer key for our final exam review guide. If you're making your way through the review guide at the same time as watching this, I just suggest every time we get to a new question, why don't you pause the video and try the question on your own before seeing me walk you through it. I think it's going to be a lot more productive than just kind of watching the video and going through the exam review guide at the same time. So without further ado, let's do it, starting with this very first problem. And this first section is all about solving equations and inequalities. For each of these, we're going to either have an equation, or we might have a system of equations in which there are two equations at the same time, or even a system of inequalities, so two inequalities at the same time. And we're going to have to solve them all algebraically. Find all those numbers that, when substituted in for the variable, makes the equation or inequalities true. If there's no solutions, we'll write no solutions. If there are infinitely many solutions, we'll write infinitely many, but we'll also indicate the solution set while doing so. And if there's a graph or a number line, we will graph the solution set too. So let's go ahead and start with this first one. So the first thing I think I want to do is I want to go ahead and distribute this -5 to this set of parentheses, g plus 1, and distribute that 2 as well. So we'll end up with -5g minus 5 equals 2g plus 4 minus 44. And then I'm going to go ahead and collect our like terms on both sides, the only ones being that 4 and -44 will simplify to -40. I think I'm going to go ahead and I'm going to add 40 to both sides of this equation. So I think I'm going to isolate all my numbers on the left-hand side and all of my, -5g plus 35. And I'm going to isolate all my variables on the right-hand side. And I'm going to add 5g to both sides. And I've got all my variables nicely on one side of the equation, 35 on the other. Awesome. When I divide both sides by 7 to isolate g, 35 over 7 is a nice number. That's just 5. So the solution to our original equation should be 5. And it's always a good idea to quickly do a mental check, right? If we substitute 5 in for g, will this be made true? Let's see, 5 plus 1 is 6. -5 times 6 is -30. 5 plus 2 is 7. 2 times 7 is 14. Minus 44 is also -30. Awesome. So it works. Just always a good idea to check your answer before declaring that you're all finished. All right, proceeding on. Same idea here. I'm going to go ahead and distribute this 3 and distribute this 5 before we do anything else. So we've got 3n plus 12 plus 2n minus 5. Got a lot of stuff going on there. 5n plus 5 plus 2. I'm going to go ahead and collect my like terms here. So I'm going to collect the 3n and the 2n, the 12 and the -5. Collect those guys as well. Just a good idea before we do anything else. We got 5n plus 7 equals, ooh, very interesting. 5n plus 7. Immediately we might be thinking, something weird's going on here. The left side of the equation and the right-hand side of the equation are exactly the same. Well, let's see what happens if we just kind of proceed onwards. So now we've got 5n equals 5n. And if we were to subtract the same number from both sides, namely 5n, we end up with the obviously true statement, 0 equals 0. And what does that mean? Well, it means that our original equation has infinitely many solutions, and not only that, it means that every real number that we substitute in for n will make it true. So the solution set is all real numbers, all real numbers. Now, on a side note, if we had come up right here with a statement that was obviously false, like 6 equals 0, then that means that there are absolutely no solutions to our original equation. All right. Number 3. Ooh, we got some nasty fractions going on here. I think the first thing I want to do is actually just take care of that 6. Let's go ahead and subtract 6 from both sides of this equation. So -6 minus 6, we end up with 11/7 times the quantity of x plus 2 equaling 55. Now, I know it's tempting to go ahead and distribute this 11/7, and you're welcome to, but to be quite frank, I don't want to do that. I'm going to have all these nasty fractions and whatnot. But instead, what we can do is to kind of negate the complicating features of this 11/7. If we multiply both sides of this equation by 11/7 reciprocal, namely 7 over 11, on both sides, well, what's really nice is on the left-hand side, these guys are going to multiply to 1. So we just get 1 times x plus 2, or just x plus 2, which is pretty sweet. And on the right-hand side, we put that 55 over 1. It looks like we have some simplifying we could do. So that's going to be a 5 and a 1. Oh, check that out. 5 times 7 is just 35. Heck yeah, this is not so bad at all. Wow, that wasn't so bad at all. We didn't have to deal with all those nasty, nasty fractions. So just a heads up that sometimes this might be a better option than distributing that fraction originally. You could do it, but it just might be a lot more complicated. Let's do a quick check to see if that actually works. If we were to substitute 33 in here, 33 plus 2 is 35. 11 sevenths of 35 is 55. Plus 6, oh, awesome, is 61. So it works. Awesome. All right, now we've got an absolute value equation. Okay, and the first thing that we want to do with an absolute value equation is we want to isolate this absolute value. There's going to be some splitting to do later, but the first thing we want to do is just treat this absolute value of 3 minus 2m. We want to treat it kind of as its own object, and we want to isolate this object right here before we do anything else. And to do so, the first thing I think we should do is add 5 to both sides of this equation. So we've got negative 2 times the quantity, or rather the absolute value of 3 minus 2m equals negative 26. Now you may be thinking, wait a second, right? We've talked about absolute values and how they can't be negative. Don't jump the gun just yet, because check it out. When we divide both sides of this equation by negative 2 to isolate that absolute value, aha, all right, these guys simplify to 1. We have successfully isolated that absolute value, and oh, the absolute value of 3 minus 2m is 13. So everything's groovy. We're going to have some solutions here. So if this number, 3 minus 2m, if that number has an absolute value equal to 13, then that number 3 minus 2m could be one of two things. It could be that 3 minus 2m is equal to 13. But it also could be that 3 minus 2m is equal to negative 13, because both 13 and negative 13, their absolute value is 13. And so now we've got two pretty simple equations to solve. I'll start with the one on the left. Let's go ahead and subtract 3 from both sides. Negative 2m equals negative 16. We'll divide both sides by negative 2, and we end up with m equals 8. All right, that's one of our solutions. Woohoo! All right, on the other side, it's the same thing. We're going to subtract 3 from both sides. We get negative 2m equals 10, and therefore m equals negative 5. All right, so we've got our two solutions to our original absolute value equation. Per usual, let's do a quick check. If m were equal to 8, 3 minus 16 is negative 13, whose absolute value is positive 13. 2 times positive 13 is 26. Negative 5 minus 26, boom, negative 31. Awesome. If m were negative 5, then 2m would be, negative 2m, or actually rather, 2m would be negative 10. 3 minus negative 10 is 13, and then everything would proceed as normal. So yes, these both check out. Always a good idea to check your answer. All right, moving on. All right, number 5. It's another absolute value equation. This one doesn't look so bad. To isolate that absolute value, let's just go ahead and subtract 9 from both sides, and we end up with the absolute value of negative 3m plus 1 equals negative 4. And immediately, when we see an absolute value of some number, I forgot that second absolute value bar. When we see the absolute value of some number equaling negative 4, boom. Absolutely, that's never going to happen. It can't possibly be the case, so we can stop right there and just say no solutions right off the bat. That original equation up top, definitely there's no number you could ever substitute in for m to make this true. All right, number 6. Ooh, so now we've got an inequality. And we got one of these complex kind of compound inequalities to begin with. So what I suggest is, there's two ways to do this, and maybe I'll have time to show you both. What I would suggest is to immediately split this up into two inequalities. We have the first inequality. Negative 11 is less than negative 2x plus 7. But we also have the inequality. Negative 2x plus 7 is less than or equal to 51. And these are going to be joined by an and compound statement. And now we've got two inequalities to solve. So let's go ahead and do it. Let's subtract 7 from both sides here. So we have negative 18 is less than negative 2x. We're going to divide both sides by negative 2. And immediately we know when we divide an inequality by a negative number, this inequality sign is going to flip. So I just kind of do this immediately so that I don't forget it later. We've got 9 is greater than x. And this inequality on the right, it's going to be the same thing. We're going to subtract 7 again. We've got negative 2x is less than or equal to 44, I believe. We're going to divide both sides by negative 2. Again, we're going to make note that this inequality is going to flip direction, so we definitely don't want to forget it. And we get x is greater than or equal to negative 22. And of course, these are going to be conjoined by an and statement again. So what I would do now is let's take a look at our number line, and let's go ahead and graph these two. So 9 is greater than, greater than x. We can also read that as x is less than 9. So we're going to put an open circle at 9. And since x is less than 9, our arrow is going to go to the left. All right. Now in green, we have x is greater than or equal to negative 22. So here's negative 22 on the number line. We're going to put in a solid circle because it's greater than or equal to, and we will shade to the right. Because we have an and compound inequality, it means only those numbers shaded in blue and green, only those numbers with both a green arrow and a blue arrow above it, those are the numbers that are going to be solutions. Which numbers are those? Well, graphically speaking, those are the numbers right in here. So we definitely want to graph our solution set, make it very clear to the reader what numbers are solutions, but then we also must state our solution set. And in this case, solutions are all numbers such that 22 is less than or equal to x, which is less than 9. So we get a kind of funky compound inequality statement as a solution set to our funky compound inequality question to begin with. So, all right. Moving on to number 7. Okay, we've got another inequality problem, but this time we have an or statement instead of an and statement. Oh, let's get that out of here. Okay, just a reminder that I'm meeting with a student later. Let's get this out of here too. Pardon me. Okay, so let's go ahead and let's solve each of these individually on their own, graph them on the number line, and see how they interact. So this first one, let's just make our way through the motions. We're going to subtract 8 from both sides. We have negative 3m is greater than or equal to 24. When we divide both sides by negative 3, we definitely want to make sure that we are flipping this inequality immediately. So m is less than or equal to negative 8. Or, let's see what else we got. Okay, this is going to take a little bit more work. Let's add 7m to both sides. I like to collect my variables and constants in such a way that I end up with a nice positive amount of m's in this case, just because if you have a positive coefficient on your variables, it's less likely that you forget to flip an inequality later. So negative 25 is greater than 5m. When we divide by 5, we are not going to need to flip that inequality. And we end up with the statement m is less than negative 5, or negative 5 is greater than m. So we're going to graph this first one in. Let's do it in hot pink. M is less than or equal to negative 8. So here's negative 8 on the number line. Less than or equal to, so there's going to be a filled in circle, and our arrow will go to the left because m is less than or equal to negative 8. In orange, m is less than negative 5. We're going to have an open circle at negative 5. And again, because m is less than, our arrow will also go to the left. Now this is an or compound inequality, which means if a number has an arrow above it at all, if it is shaded in orange or pink or both of them, it's a solution. In fact, the only numbers that aren't solutions are these numbers way out here on the right because they don't make either of them true. So graphically, our solution set are going to be all these numbers here. Every single one of these numbers will make at least one of those individual statements true. So they're solutions to the compound inequality. Again, we want to explicitly write to our reader what the solution set is, and that solution set is all numbers such that m is less than negative 5.